Welcome to the UEI Technical Masterclass. I hope everyone's doing well today. I'm Bob Finn with UEI, and in today's webinar, we'll be covering reliable onboard monitoring and verification for your system. This is meant to be a somewhat informal briefing and Q&A session to cover various concepts. Whether you're in the field or laboratory environment, the ability to quickly and easily test a system as well as to detect a fault for rapid resolution is critical. With this in mind, we'll discuss our sophisticated and reliable onboard monitoring diagnostics we call Guardian, also known as built-in test or BIT. This is not only a presentation, but an opportunity for you to ask us questions about this topic. And don't be shy. Send us your questions with the chat box located in this webinar window, and we'll be sure to answer them. And speaking of questions, let me introduce you to our UEI applications and engineering team. From the top, we have Timur, who wants everyone to, quote, live dangerously by using the auto set button. Next, we have Austyn, who will be presenting today. Austyn is a seasoned application engineer with an expertise in embedded devices. He's also an avid hiker and a bad flight simulator pilot. Moving down the list, we have Brian, who believes every question is a good question. Next is Phil. Phil wants everyone to know he agrees with Brian. Knowledge starts with the first question. And rounding out our roster of application engineers is Prabhu, joining us from the UK. He specializes in solutions, workarounds, and fixes. His mantra, keep calm and carry on. So that's our team of experts. And as I mentioned earlier, Austyn will be reviewing the concepts this morning. So I'm going to hand it over to Austyn.
Thanks for the introduction. As Bob mentioned, my name is Austyn Turner, and I'm an application engineer here at UEI. Today we're discussing onboard monitoring and diagnostic tools, which we call our Guardian features. So let me share my screen. So before we go into the videos, let's talk about what are these Guardian features exactly. Well, they're not any one defined set of features, but they're really added diagnostics to become more aware of the system and the environment. Specifically, what we're looking to identify are fault conditions, which can be open broken sensor detection, self-testing of inputs, or possibly voltage and current monitoring to help identify these and other conditions. Throughout this class, I'll be talking about real-life applications and try to show the power of using these Guardian features. One of the fields we can address with these added diagnostics is we're really able to narrow down issues more quickly, so allowing for rapid resolution of fault conditions. An example of this would be open circuit detection for thermocouples. So for those who don't know, a thermocouple is a small voltage temperature sensor, and 0 volts is a completely valid reading. So when there's an open circuit, a system might not be aware and it might report a false temperature. On our analog input side, we have open circuit detection. So the software can identify and raise an alarm upon an open circuit. We can also flip that scenario and say we are simulating a thermocouple. Well, our output will both want to simulate the open circuit and also identify that open circuit in case it's not caused by our board, but rather a broken wire. So this is just one application with one specific set of boards. We have a variety of Guardian series boards, and I'll try to cover some more of them throughout this class. And with that said, let's step into the first video.
At UEI, we know that a single flaw in your system could spell disaster. That's why we've built the Guardian series to protect you from something like this. From the chassis, to the board, to the channel, Guardian monitors your whole system, detecting faults and providing real-time diagnostics. Our compact, rugged hardware operates in places you can't, so it works anywhere you need it to. And With built-in remote access, you can get your data quickly and easily. We offer a wide variety of system options to cover almost any application. Many of these include our built-in Guardian features. So, when you need to guarantee your system integrity, you need UEI's Guardian Advantage.
So that's just another intro to the Guardian series. Now let's take a look into, again, a specific application where these Guardian series can be used. And after this video, we'll take a minute or two to start answering some questions, if any questions have arisen. Hi, my name is Austyn Turner, and I'm an application engineer here at United Electronic Industries. Today I want to talk to you about UEI's implementation of pulse width modulation. Pulse width modulation, or PWM for short, is a technique used to pulse a signal at varying widths. This is used in a variety of applications, such as motor control, power delivery, light control, and more. The PWM signal is characterized by its frequency, amplitude, and its duty cycle. The duty cycle of a PWM signal is defined as the percentage of one period in which a signal is on. As you can see, the larger the duty cycle, or on time, the larger the average voltage over one cycle period. At UEI, we support PWM applications with our DIO 432 and our DIO 433 boards. They are PWM syncing and sourcing boards, respectively. The Guardian features on board are a set of powerful diagnostic tools, allowing you to measure the current and voltage on each individual channel. Each channel can be configured with high and low current limits and can act as a circuit breaker if the current passes these limits. Here I'll be demonstrating using our DIO 432 board in a LabVIEW application, controlling these incandescent lights. Here is an equivalent circuit of the setup. 28 volts DC connects to one terminal of the light. The other terminal is connected to a channel of our syncing PWM board, the DIO 432. The DIO 432 acts as a switch to complete the circuit to the return line of the power supply. UEI has built-in functions for controlling these lights. These are our soft start, soft stop, and soft start and stop functions. In this example, I'll be showing the soft start option for the lights, which is useful for limiting the on current of incandescent bulbs. As you can see, the lights gradually turn on until they are at max duty cycle. This next demonstration will show the lights at varying duty cycles. The lights are at 25%, 50%, and 100%. You can see that the higher the duty cycle, the brighter the light. This final demonstration will show the circuit breaker functionality of the DIO 432. Incandescent bulbs have an inrush current that is around 10 times the normal on current. By monitoring the current, we can set a max value that, when crossed, will open the circuit similar to the action of a circuit breaker. You can also set a retry rate to attempt to close the circuit in case the high current has faded. I've set my current to monitor at a faster rate than before so that I can capture that quick inrush current, and I've also set my current threshold to 1 amp. Using soft stop mode, you can see that when I activate the lights, the current spikes and trips the breakers. The retry function closes the circuit, causing a continuous cycle of the lights starting and tripping the breaker and then retrying. You can download this LabVIEW example and more from our website. Got a question about pulse width modulation? Give us a call, send us an email, or visit us online at www.ueidaq.com. All right, so I know we just got into this, but there was a couple questions that came in, so I'll answer those, and then we'll try to look at a different use of that 432 and 433 board So we can dig into more real life applications of where they're used. But one of the questions that came in is, what's the max rate of PWM that you support? So for those boards, we support up to about 10 kilohertz of PWM. But if you need something with a higher rate, we have counter timers that will output a TTL level PWM, and those will be, I think, upwards of 100 kilohertz. I can go into specifics of that by looking at the manual or the data sheet for those boards. Let's see. Are there other boards that have circuit breaker features? Yes. So one way to identify those features is, and we'll go into how you can identify how to figure out if your board is a Guardian board or not. But the data sheet will have a lot of that information. So some boards that we have circuit breaker features, 432 or 433, mentioned in that video. AO 318, which we'll take a look at later in this masterclass, and certainly some other boards out there as well that we have. Another question, how fast can the breakers trip? That depends on how fast you're monitoring the current. So the example there was 200 hertz. That'll be somewhere in a few milliseconds that will trip. The nice thing is it's not the application that is tripping the breaker, so it's not something that needs to continuously pull. It's a setting that you set it for that overcurrent rating, and you set the current measurement rate, and the board itself within the FPGA will be monitoring the current and will trip as soon as we can detect that overcurrent. So another question. So there are other boards that have the PWM mode. Yes, so 432 and 433 support PWM. Our counter timers support PWM. And then you can use PWM with other more general purpose digital outputs, but that would be more software driven, whereas the PWM that the boards I mentioned, the counter timers and the 432 and 433, are built in where it makes it very easy to set a PWM. Another question, can you acquire and monitor voltages and currents over time to see the current that affects the trip event? Yes. So what we're doing when we're monitoring that current is we're monitoring the current that's flowing within that circuit. Even when we trip, we can still monitor the current and get that value in our application. So we can see when the current exceeded the trip with some delay. So we might not see the exact value that it tripped at because the trip might occur so fast, but we can see before and after the trip event. Another question, can the board start up in circuit breaker mode, or do you need to make a library call first? That's a good question. We have certain settings that can be stored in the board upon initialization so that they will always start up in that scenario. For example, a digital output, you can store it to always default to on. For circuit breaker mode, I think it's safest to have your application do it. I'd have to check to see if we can store all the values. But again, there's a lot of different settings you can use for the circuit breaker mode. So I think it's safest to put it in your application and have a library call first. Okay, so let's move on to a quick PowerPoint presentation. So let's see if I can get this going right. So this is an excerpt from a webinar we had given a presentation in 2017. So what we're looking to do is outline this issue. How do you build a test system that avoids failure and ensures final system success? Well, let's look at a scenario where failure occurred and how it could have been avoided. So in the picture here, we have the Deepwater Horizon. For those not aware, this was the BP oil rig. It was located in the Gulf of Mexico, and in 2010, it experienced a catastrophic explosion, caused 11 deaths, 17 injured, and over $61 billion in liability losses. So how could this have been avoided? And what was the root cause? Well, there was a sequence of events that occurred to make this happen. But the investigation that was released in 2016 showed some of the major factors. And one of the major factors was this BOP, or blowout preventer solenoid control. So a blowout preventer is used to contain uncontrolled release of oil. It has two redundant solenoids to actuate hydraulic and mechanical shutoff. They have battery backups in case of loss of power from the top side. So what happened on the Deepwater Horizon is on one side, the solenoid was miswired, and we can see the main battery was shorted. So the main battery is dead. On the other side, again, there was a miswiring, so we have another dead battery. So the operator had no idea of these conditions. There was no diagnostics and no checks to ensure they were wired properly. If we take a look at those subsea electric modules, we'll see they're basically just switches. So there's no extra information that can be gathered. So again, this catastrophic failure, a sequence of events, and we find two major issues of a miswired solenoid and a dead battery. Well, the video we just showed talked about the 432 and 433. Now, I know some of the circuitry is maybe too small to completely make out. You can see those circuits and the data sheets for those boards. But the main concept is using that voltage and current sensing to avoid these types of conditions. But when they can't be avoided, to troubleshoot them before they ever happen. So if we think of the voltage sensing, so we had one battery or both batteries that were shorted. Well, with voltage sensing, we could have detected that. So prior to this catastrophic failure, we could have identified that the battery was shorted. Now we know if we replace the battery, now we know that's working. But how do we know the solenoid is actually working? Well, now we can use current sensing. So we've activated the solenoid. We're watching the current as it flows through the circuit. If no current is flowing, we know we have another issue. If too much current is flowing, we might have an internal short or a stuck solenoid. So these extra diagnostics really help to, again, as I led to in the introduction, become more aware of the system. So let's build a checklist. Let's look at methods to sense and diagnose failures with our Guardian features. So one thing is to ensure the tester is tested. And this is very important because time and materials add up quickly. When you're constantly debugging, troubleshooting cable issues, broken sensors, that leads to a lot of downtime. So we need to find ways to troubleshoot that so we can either fix it before it ever happens, or when it does happen, we know where it's occurring and can fix it more quickly. And we want to lower that mean time to repair, the MTTR. So the first one would be a wire's not connected. Now, sure, if we say a wire's not connected, that could be an open circuit, but let's think of short circuits as well. So we want to try to identify those. Output voltage is at the desired level. A simple analog output, you would expect to just output the voltage that you've programmed it to. If I say output 6 volts, I expect 6 volts. But if the load has changed, then you might not see that same voltage. If you're trying to output 6 volts into 1 ohm, you might be shorting your analog output. So we want to try to detect that scenario and measure the output voltage, but we don't want to add extra wiring. We could take an analog input and wire it to that analog output, but again, now we're taking an extra channel and we're adding more cabling. And the last would be, is your analog input working? I expect to see 6 volts in this input. I'm not seeing 6 volts. Well, did something happen to my analog input board, or did something else occur in the field? One way to approach this problem would be to test the analog input internally to make sure that it's functioning still. So we have boards that, even while the field wiring is still connected to the board, we can switch to an internal reference and we can verify the analog input is working. So this is where I would open up for questions if any have come in. If not, we'll step into the demos I have to show each of those 3 scenarios. So let's see if any new questions came in. Okay, I see one. How does open circuit detection work? So I don't know if all open circuit detections are equivalent, but the main concept is to put a very small current, in the nanoamps into the circuit. So when the circuit's completed, that small current does nothing. When you have an open circuit, whatever voltage is driving that current source, that's what you're going to see on the input. So for thermocouples, if you have a small current in the nanoamps, but it's driven by maybe a 1 or 2 volt signal, you're going to be driving that input to that 1 or 2 volts or to the rails. So we can really quickly identify an open circuit once it goes to that voltage source value. Okay, I don't see any more questions yet. So let's step into a demo. Okay, so what I have here is one of our half racks with 6 boards, all of them having Guardian features. So we'll try to go through each of those scenarios and really step through how would one of our boards, how would the Guardian series help to identify that. So the first was the open circuit detection. So here we have our DIO 449. If you're not familiar with this, I'll go over some details, but you can also check the data sheet for this board. So this board was created with a specific application in mind. So we work in maintenance trainers. Whether someone is being trained to work on a helicopter, a plane, or anything else, you're going to have different voltage levels for signals. They could be 5 volts TTL. They could be 10, 12, 28 volts. And when you talk about avionics, you're also going to see 400 hertz AC signals. Now, again, I mentioned this is a maintenance trainer. So you're going to have someone who's being trained and connecting wires to different places. Of course, if you connect 400 hertz to a normal TTL input, you're going to blow up the board. So we created this DIO 449 as basically an indestructible digital input. But not only that, we're able to handle both DC and AC inputs. And we can see here in Power DNA Explorer, which again, we have some some other YouTube videos demonstrating Power DNA Explorer if you're not familiar with that. We can see that we can change between DC and AC input. But really, part of the Guardian is being able to set the low and high threshold on each individual channel. So when you're working with 5-volt TTL, 28 volts, and that AC signal, you can program each channel independent of the other. That way you can handle all the signals within a single board. Now, I mentioned we want to detect open circuit. Well, if I start reading on this board, we'll see we have some negative voltage. And that's how we're detecting this open circuit, is we're expecting to see some voltage on the input, but we have a small current that we're injecting. So when we see this constant -3 volts, we can identify that as an open circuit, and we can raise an alarm condition, which again, in your software, could be a varying level of alarm. Could be, this is okay, but we need to fix this upon the next test, or we need to shut this test down, and we need to go check out what's causing the issue on channel 5 of the DIO 449. Now let's step into the next scenario. And that was, we'll jump to the third one, checking your analog input is working. So here I have our AI 218. I have a self-test adapter. Again, you can check our website. The main idea of the self-test adapter is to quickly test an input board or quickly test really any of our boards. So what this does is it injects a voltage into each channel. So I can see I'm reading -5, 3, and so on each of the channels. Now I'm going to run some C code. And with the adapter still connected, we'll see that I can connect the 5 volts to the input and really test that the board is working. So let's go into a code example. And so what we're going to do in this example is we're going to run through a few iterations, and we're going to see the same -5 and, I forgot the voltages, -5 and 3.7 volts. And then we're going to switch on that internal test. So I won't go through all the code, but the general setup occurs, and then we get to our while acquisition loop, and we see we're reading the voltage, and I've configured the built-in test mux to switch the 5-volt input after 5 iterations. So let's give this a run. And it came up on my other screen, of course. So again, we see that the -5 volts and the 3 volts are occurring just as before. And now we're going to enter the self-test. And so right away, we see I put in that 5 volts, and I'm reading very close to 5 volts in every channel. So we know the analog input is working. Again, this is just a demonstration, but in your real-life applications, it can be very powerful to help identify where the problem is occurring and where the problem isn't occurring. So let's stop that example. So one of the questions, again, that came in is, how do I know this board has Guardian features? So there's a few ways to identify. One is, you can always contact our support team. It's support@ueidac.com. And we can definitely help identify which of our boards our guardian. One of the main things we do as well is our quick reference guide, which highlights the guardian in gray. So I was prepared for that question. So I have our quick reference guide here. Let's scroll down and we'll take a look. So the board that I just showed, AI 218, so we see that that's highlighted in gray. And we could keep scrolling down through and we'll see a lot of our boards that have that gray. So we offer the normal, digital inputs and outputs, but we also offer these Guardian series so that you can get those extra diagnostics and really become more aware of the system. Again, just hammering in on the troubleshooting and limiting the downtime of when an issue occurs and identifying where that issue occurs. Okay, and then one of the last demos was let's see, go back to that PowerPoint, the output voltage. So as I was mentioning, we want to identify the output voltage is actually at the value we programmed it at. So we have this AO318. Now, I'm not sure if I'm allowed to mention who this was created for, but again, we create boards with an application in mind and with a solution in mind. We could add these features to any board, but really we're adding them to solve a problem. So the AO318 was developed for a space exploration company. And what they needed was a voltage output that they could also monitor the voltage and current. So again, you're outputting this voltage, but you're really almost as a double check to verify that that voltage is occurring. So if we try to output 6 volts, we better measure that it's 6 volts. And if it's not, then we know there's an issue. If we output 6 volts and there's no current, then again, we know there's an issue. So what I have here is the AO318, and I had already programmed to 6 volts. Let's change that to 3 volts. And let's start measuring. So we can see that I don't have anything connected. And even with nothing connected, we can measure the voltage from DAC A. Well, what is this DAC B? This AO318 not only has the voltage and current monitoring, but also a redundant D to A converter. That way, if one trips for some reason, say in an overcurrent condition, you can go to that backup D to A converter and still output the voltage that you're trying to output. Again, we're trying to provide a solution to the problems that this customer needed. Now, I've gone over some details of our Guardian series. You can check out more on our website. So the Guardian series tutorial reference guide gives some more information about the boards that support the Guardian and what those features are. One of the things I haven't gone over is the ability to loop back serial protocols. So one in mind is the ARINC 429 protocol. You can be transmitting a message and at the same time on that same board receiving the message that you're transmitting. And it's really helpful to identify and even self-test the board, because again, we want to make sure that what we're outputting is actually being output on the field wiring. And now we'll open up to any final questions that are coming in. Okay, it looks like no more questions. Thank you all for attending, and Bob, you can take over again.
Okay, thank you very much, Austyn. That was a great presentation. I want to thank everyone for participating. We'll be contacting anyone with unanswered or partially answered questions. And If you want additional support or you've got an idea and a suggestion for another technical masterclass topic, please email us at support@ueidaq.com or call us at 508-921-4600. Looking forward, we'll be continuing our masterclass series at the same time next Thursday. As you see, May is Avionics Month, so we'll be taking a deeper dive into the world of MIL Standard 1553 and ARINC 429. And it's also worth mentioning that we record every webinar and we post the video online the same day. You can watch any of our previous webinars either on our YouTube page or on our own webpage, ueidaq.com/videos. And that about wraps it up. So I want to thank you again for joining us, everyone. And we hope you found this webinar useful and hope to see you again next week. And until then, please stay healthy.